So hi everybody. I'd love to introduce Chris Rokakis from MIT and SciML, who is trying to automate the scientific process. Welcome, Chris.
Yeah, thank you very much. Yeah, so today what I want to talk about is how differentiable simulations in SciML. So essentially, how does differentiation of simulators come into play for scientific machine learning, and then lead to the automation of this model discovery in the physical, in the way that we understand physical laws, right? So this is going to be a pretty high level talk. I'm going to go through a lot of different cases pretty fast. We're not going to go into too much mathematical detail and everything. If anyone wants to go into any detail, we can go through and discuss in more detail. But I really want to kind of paint a whole picture of what we're doing with all the work in the MIT Julia lab in the SciML organization. And I want to say, at the start here, that there will be a lot of different benchmark numbers that are thrown out. We keep a open benchmarking platform. This is the SciML benchmarks. You'll see that a lot of these benchmark results can be found here. And so if you're interested in any of the numbers, how they're calculated and such, you can always refer to the code here. Let me get started then on the meat of this. So the core of what we're doing is what we call scientific machine learning, right? This is a term that was coined in 2018 by some groups. They were DOE groups, Department of Energy, at this workshop. And the idea behind scientific machine learning is to use the information that we have as part of the modeling process, right? So, normally when you think about machine learning, you normally think, data, right? What data do I have? If I have enough data, then this thing will be able to predict well enough, right? Now, when you think about the physical modeling process, you could think, well, okay, what do I know? I know Einstein's theory of relativity. I know these things about chemical reaction networks. I know that these chemicals connect. I know that these ones don't. And you have all these kind of structural information that you build models out of, these mathematical models that are then predictive if they are correct, right? Now, the key of what we're doing with scientific machine learning is we are merging the two of those, right? We're basically coming up with ways of saying, we know this much information about this subject. We can encode it inside of our mathematical models, but we know that there are some things that we don't know, right? And by doing so, we hope that this can be something that's more data efficient than just purely data-based machine learning, right? And that's really the key behind scientific machine learning. And I'm going to show a few examples of scientific machine learning methods achieving that goal, and some of the ways that we're then trying to continue to push this subject by allowing more and more types of models and more types of prior information to enter this kind of process. And so my core point here, the core thesis behind this will be that differentiable simulation is hard. In fact, it's a way more difficult software way of achieving scientific machine learning than some other methods for doing this. But it's definitely worth investing more time into, because we will see that the methods that are using differentiation are really well grounded in they're just really well grounded in what they're trying to achieve, and the results that we get from techniques that use differentiable simulation just keep outperforming the other kinds of methods that we are testing them against. And so the starting point for this to kind of understand where are we going with this idea of mixing models and data. This universal approximator differential equation is this one kind of jumping off point. So it's the key idea behind it is that universal approximators are these objects that are able to model functions. Think a neural network is a way of representing an arbitrary Rn to Rm function, where if you have certain properties in the activation functions, this function can be, say, smooth, and so then a neural network can be approximating the set of smooth functions or the set of positive functions, right? And machine learning can prove, this theory can prove that these things can be approximators for a full set of a function space, right? What we can do then is we can add these to our model to be able to capture functions that we did not know about. So we can begin to say, so for example, a lot of modeling occurs with ordinary differential equations, right? And so if we have an ordinary differential equation for our model, we might have left off some higher order physics, right? It's very common when you do physical derivations that when you hit the, when you're doing your derivation, you cannot write down the entirety of your equations, but as you do that derivation, you say, there's some higher order terms. If they're approximately zero, then I get this resulting equation, right? And this happens all the time. But now what we can do is we can say, well, we can write down the physical equations that we know, but we can also understand that they're approximate. In our physics, the cows were they're spherical, and there was no air friction. There was no friction in the air, and all these kind of assumptions. We can say we know that our model is not completely correct, but let's write it down and then say plus, there's some extra terms that we have definitely left off here, right? And so this universal differential equation is essentially this technique of doing different modeling processes by using universal approximators as part of the modeling flow. And to really kind of see why this is something that is an interesting step towards this, scientific machine learning, I really like to break it down example by example. So what I'm gonna do is I'm gonna show you that this workflow gives you something where each step of the workflow really extracts out more information. So the workflow is you start with a model that you write down all of your known relationships, and then you have these unknown relationships that are captured by a neural network, right? This plus neural network kind of piece inside of the model. What you do is then you train the neural network so that way the the parameters are optimized, but then also the neural network is capturing the unknown parts of the equation that are required in order for the simulation to fit the data, right? And once you've had this version of the simulation, which is modified by a neural network and it fits your data, then you can start to analyze, what was I not modeling, right? The way to analyze what you're not modeling is you pull back out this neural network. You begin to ask it questions, and one of the main questions we see people ask is you doing symbolic regression. So what is a good symbolic approximation to this piece that I wasn't modeling, right? And then what you get out in the end is essentially this kind of form of autocomplete where you have the terms of the model that you knew, and then you have these new terms of the model which are constructed or guessed by this neural network that is in approximating what you did not know had to be in there, right? And I really like this example where that we did at the very start of this process. So very early on into the SciML organization, COVID happened, right? And so we did do a lot with epidemic modeling, and we had a series of papers on epidemic modeling and how the SciML techniques can improve them. But I think that if you kind of just go step by step through the process, it really flows more than all the paper results. Just kind of looking at the steps of the process really shows you how each piece makes its contribution, right? Because the starting point of this is, well, what if you did not assume any prior information, right? So if you did not assume any prior scientific information, then you would have what's known as a neural ODE, right? This is U prime equals a neural network, which basically says, this continuous system is governed by a neural network. We don't have any prior idea on what this ODE can look like. And what we did here was we trained this from 0 to 21 days. And where you see that black line is where the training data ends. It extrapolates forward. And a neural ODE with that information at the beginning of the pandemic does not extrapolate. And I don't think that anyone would be surprised. I made sure to put down, like one example paper that shows that we know that neural ODEs don't extrapolate like the scientific model, et cetera, et cetera. But there's many examples of this. But I think that the key idea though is that there's no reason for the neural ODE to extrapolate correctly, right? We've only given it 21 days worth before it's seen an exponential growth. How does it know that the future is supposed to be doing exponential growth, right? We know that a epidemic that is spreading will likely have an exponential growth phase, but there's nothing about our neural network architecture that has encoded that should be the case, right? And so what we can do though is we can build a neural network architecture that has a lot of the principles of an epidemic model from the start. And so this is where we get to this universal ODE form of this epidemic predictor, right? So one of the key things about such a form like this, so here this is an extended SEIRD model, right? So one of the interesting things with this kind of model is that there's a lot of prior information that we can encode even into the parameter values, right? So for example, with an SEIRD model, there's information we have to put in here, like what is the percentage of the individuals who get the disease, which are not, which do not have to go to the hospital versus which have to go to the hospital. What are the percentage of the individuals who died from COVID, right? Now, all these things show up as parameter values in here, but we don't necessarily need to learn them from the time series because there's other information out there that can motivate a lot of these values, right? And when you do the modeling process, this is how you come up with a lot of values, right? You go check the statistics. You see, for example, mu is motivated as the percentage of individuals who recover without ever going to the hospital. So therefore, this. You can come up with that value by looking at the hospital occupancy rates versus the expected disease rates, right? So there's a lot of information we can get, and there's quite a decent model that we can build with just outside information. So what we can then do is we can then make better use of our time series, right? Our time series can then just be used to be able to capture things that we did not really know how to model. And in the case of a COVID-19 model, there's a very good part that we don't know how to model, which is exposure, right? Because exposure to COVID-19 is dependent on, well, are the people in your area wearing a mask? Do they happen to be, wearing a mask? Were you in China versus India? Right? There's all sorts of different regional differences that lead to differences in the way that people got exposed to the disease. And coming up with one mathematical function that is, COVID equals, proximity to Italy during the month of March, et cetera. Like coming up with a full model for that one portion can be very difficult. And so what we can do instead, though, is we can say, well, this is a mostly known model. The part that we don't know how to model, that we can make that, that exposure term be a neural network. And then we can use this as our predictive model that we, train the neural network on to capture this exposure, and then we extrapolate to the future, right? There's a few things that you can see. Yep.
Federico? Oh, you're muted right now. Think. Okay, here. Okay, we'll come back. Yeah, go ahead.
All right. Yeah. So there's a few things that we can get from the structure, right? So one of the interesting things that comes out of this is, not just that it extrapolates better, which you can see over there, but I think that the more interesting thing is that there's a lot of structural information that's encoded in this form, right? So one of the key pieces here is that, if this neural network is guaranteed to be positive, we have conservation that's enforced, right? So we're doing minus s at the same rate that we're doing plus e, and so therefore we have conservation of people within this model form, right? So the standard ODE does not necessarily have to conserve the population, whereas this has conservation built into the equations, right? And so there's certain conservation laws that are imposed in here. In fact, if we enforce that this neural network is positive by taking the absolute value of its output, then we can actually enforce that, for example, S is always decreasing. And so then, we're going to have a certain, you can then prove that there's a maxima to this equation, right? And there's one wave if you don't have reinfection. And so there's a lot of properties of an epidemic that we're really imposing just by having this very simple mathematical structure around it, right? So the key here, I think.
Can you hear
Yep.
me now? Okay, excellent. Chris, I meant to ask, is it okay to ask questions in the middle of the talk, or do you prefer them all at the end?
Totally fine. Yep.
Great. So I think a few of the scientific ML papers that I've seen, they basically generate the ground truth from the model, sample the output of the model at a very high resolution, and then fit it, and everything works very, very well. When you're working with real data, one of the problems is that even a mechanistic model is typically massively unidentifiable. So you never have enough data to actually identify the parameters of an extended SIR model from real world data, just because there's so many things that you don't actually observe, or you have really noisy things. How do you think about adding, complex terms that are very data hungry when you're in a regime where you can't even properly identify the parameters of the naive mechanistic model?
Yeah, I mean, yeah, that's a good question. I mean, so one of the things that comes up in this, yeah, so when a lot of times when you do this with real data, right? One of the things that is interesting is right. So I think the thing that's interesting is that when you're looking at identifiability, right? Generally, you're wondering about parameter identifiability, right? So you're like, are there multiple different parameters for my model that can also fit this data, right? And you know that almost by definition with these neural networks, they're not identifiable, right? When you start to go to this the scientific machine learning sense, there seems to be a different definition of identifiability that we start to care about, right? Which is this idea of, is there a, it's not whether the parameters are identifiable, it's whether this unknown function is identifiable, right? Are there different functions that I could have put in here such that I could also recover this piece of information, right? A lot of what we've been doing recently is there's this recent paper on sorption models in chemical process modeling, where what we did was we looked at on noisy generated data in a partial differential equation form. If you do this and you do this in a very kind of messy, complex environment, what kinds of functions do you pick up? And what we find in that case is you aren't always able to get back the correct unknown function. But what we do find in a lot of these cases is that it can capture, say, the first and second Taylor series approximation terms, right? So, you can't always find the right function there. But if you take the first and second term of the Taylor series of the unknown function, and you do that, and you check it against the version that is in the one that generated the data, you see that there's a correspondence, at least in the lower order terms, right? And so, yeah, I mean, so we are saying that there's something about functional identifiability that seems to be able to hold even if you don't have metric identifiability. Now, what are the ways of being able to know when you have functional identifiability? That is not something that we've really worked out yet, but it is something that we are going a lot more towards. Now, yeah, so I mentioned that in a generated data case, I mean, the reason why a lot of people use generated data for SciML, so that way you have a ground truth. I'll mention a lot of cases that don't have a ground truth in a few slides here, though.
Okay, no, I was also specifically curious about the case where you are, as you mentioned, you're going to talk about the case where you don't have the ground truth, but where the data that you have is woefully inefficient to fit the mechanistic model. Do you think in that case, it's still valuable to add a neural ODE term if you're not able to even fit the mechanistic model by itself?
That I'm not sure about, right? I think that in those cases that there's two things that we know I've been using in practice. I'll probably not mention too much, but one of the things that we do a lot of is, if you know about the quantitative systems pharmacology literature, there's a type of methods called virtual population methods, which are all about quantifying the uncertainty of parameter estimation processes. Using that as one way to be able to then give a nice uncertainty quantification of of this unidentifiability. And so we've been going a lot in that direction. The other thing is that the other thing is that using these techniques as a stepping stone is, I think, what's more important for a lot of scientific practices than using them as a predictive model. So, I'll mention right here, right, that, the next thing that we then do with the universal ODE a lot of this time is do something like an internal sparse regression. And what we get with the sparse regression is it kind of tells us which places our model are likely incorrect. And the reason why this is interesting is because if this is something that is, say, a chemical reaction model, right, then this is telling us what's most likely chemical reactions that we did not know about. And we could go back into the lab and see, test for these chemical reactions, right? And so you can almost think about it as a a guiding process for the scientist rather than something that you're merely using for the predictive power, right? So I tend to think that aspect is really the most important aspect. That it's giving you a prediction of what could be missing in your equations, and you can then say, okay, if this could be missing in my equations, then what did I get wrong about my derivation? What did I not know about the chemistry? And then you can go back and check for those pieces. And I think that that's much more valuable than just the pure extrapolationness. People will focus a lot on extrapolated performance because NeurIPS or whatever want like the RMSE, the lower the prediction error is easy to review. But I don't think that that's really the key of why these are being used a lot in the scientific practice these days. Does that answer the question?
Yes, thank you.
All right, yeah. So I'll just continue it then right from there. So when after we learn this unknown portion, right? You get a lot of nice properties because we've encoded a lot of prior information into the model. But then the real next step is you can start to analyze. What did I not know in the model? And as I mentioned, you can do say a sparse regression, and that sparse regression or other techniques like doing a sensitivity analysis of this neural network can tell you a whole lot about what you did not know about your modeling process. So when we did this example, we actually allowed this neural network to be a function of S, I, and D, right? So we said exposure can be a function of susceptible, infected, and dead individuals, right? And when we do the sparse regression, it tells us that the best fitting lower order polynomial to what the neural network had found is something that is a function of S and I, but not a function of D. Right, U3 does not show up in that equation. And what this is really, what you can interpret that is saying, well, if this portion is supposed to be the exposure term, right, then this is a prediction that exposure is not a function of the number of individuals who have died of the disease, which makes sense because people who have already died are not the ones who are spreading the disease, right? It's the ones who are infected. And so, you can if you have basically the idea behind it then is that really nice thing about this kind of technique is that once you can kind of hold on to, you basically have a computational representation of what you did not know how to model, you can start to poke at it and ask it questions about, what is the most likely thing that I could be adding to the model that would improve my model's ability to be able to handle this new data, right? And that's where I think it's most valuable. For one other piece that comes out of this as well that we found is that generally after you do the sparse regression, you tend to see improved generalizability, though that seems to be something that we do not have a good proof for that it happens in general. We have seen this kind of case by case by case, and it's kind of this mystery that we're still kind of looking into. But now yep.
So if I may summarize what you're doing here is you're making a science debugger. My science is wrong. I'm debugging it so I can make better science.
Exactly. Yeah. Yeah.
Yeah. So then the challenge of that, I mean, the term here is interpretability, that people across everywhere say like, one interpretable model, even if it's wrong, which is sort of weird to anybody with a computer background. Why would you want the wrong model? So what I'm really going to be asking about is there is this underlying idea in this COVID stuff. There's an agent-based model that's just too complicated to parameterize and run. And this is a shadow of that model. And so you can show this to people and they can sort of understand it. But if there is this underlying quantum simulation that's in their brains, or an agent-based model, is there a way of connecting it farther to say that this is a good approximation of your underlying really expensive model that's informed by, well, my debugger?
Yeah, I mean, I'm going to get to the connection with agent-based models. And actually, I'll be at ICLR in a few weeks, and I'll be specifically talking about the agent-based model piece. That's where if we could differentiate the agent-based model, we can actually use it to be able to try to discover the ordinary differential equations that approximate it. So I'll try to get to mentioning that part.
Okay.
Yeah. Yeah, so for now I'm starting on just ODEs because it's simple, but if the real key here is that if we could differentiate all different types of simulations, then we can start to train these approximate models over kind of any of them, right? And I'll get to how we're doing that as well. So I'll punt on that, but please come back to that. Yeah. So I think that the interesting thing with the universal this universal differential equation kind of technique is not necessarily just the results that we showed early on, but the way that people kind of took the idea and the software and really brought it to a lot of scientific disciplines and showed that on a lot of non-trivial cases that it was working out. I like this. I really like this case from this group that looked at this binary black hole system. Well, what they did was, shortly after the LIGO experiments, found this gravitational wave data from this, binary black hole system, right? They looked at this and said, well, it requires relativistic corrections. You can't model it with Newtonian physics, but this is a case where you can write down, Newtonian physics in a rotating frame, which is, equations 5a and 5b plus neural network terms, right? And then the question would be, well, how can you have this discover, what the relativistic corrections to Newtonian physics would be in order to be able to, predict the motion of this binary black hole system, right? And for this case, they used just the black training data, and then they extrapolated forward, right? You can see that the orange is the predictions, the blue is the true waveform, and they're able to extrapolate out quite well, right? And in a way that generally wouldn't assume that machine learning would kind of do with that amount of data. Now, in a relativistic context, we know general relativity down to 12 digits of accuracy. The scientific machine learning model does not give you 12 digits of accuracy, but it gives you something like 5 digits of accuracy, which if you're just thinking about machine learning, ChatGPT, 5 digits of accuracy is pretty good, right? So it's almost like hitting you somewhere right in the middle there. And if you go look at this up and you Google this around, you'll actually be able to find a notebook for how this is done with their data, and the notebook that trains in like 5 minutes or something, and so you can fully recreate their result here pretty simply. So we've been using this actually as a teaching example now, as one of these cases where it's been very very useful, right? I think a case that we found in the literature that is a very nice demonstration of why this is interesting is this case that came up with the structural identification for earthquake-safe buildings. Essentially, what this team did was they took this data from these kind of fake toy building model simulations, and they first built a model of their system, which gives these results that are the dotted lines. If you look really closely, the dotted lines don't quite extrapolate out well, so they knew that their model was not quite correct, but they were able to then augment it with the plus neural network, and this improved the extrapolation properties. But then once they had that, right, the interesting thing is not necessarily that they could extrapolate better, but the neural network was telling them where the models were not necessarily correct, which would then help them be able to go back and correct their models to then kind of know, what pieces of the model are actually useful to understand if you're trying to make a building that is better and more earthquake safe, right? So this is just another example. Yeah.
It was the original model, a physics-based model that you were improving?
Yeah, and they built this physics-based model. I think it was a multi-body dynamics model, and then they extended it with the neural network. Yeah.
Okay, so it was a partially incorrect model that you actually debugged in the sense of improving the model.
Exactly. Yeah.
Nice.
Yeah, so I do have a older video on YouTube where I go through many of these different case studies where there's kind of hundreds of them at this point. So if you go to this YouTube video, I walk through a whole bunch of the different cases. But I think that the point here is that I first motivate this using generated data and a simple example to show how it comes together. But there's a whole lot of different people who have now been able to replicate this on real systems and showing that the same principle keeps applying, right? So I think the thing.
Federico?
Chris, I think in some cases, you can be very confident that the theory part of the model that you write is correct and you really trust it. In some other cases, and here I'm thinking like bio, where I know you've done a lot of work, the ground truth part of the model is often extremely optimistically say, let's say, approximative or heuristic. How robust are those recovery methods if you completely, like, to what extent can you misspecify the mechanistic portion and still recover something useful? That's the spirit of the question, I guess. Yeah.
Yeah, so one of the things that was interesting, so there's a YouTube video from JuliaCon 2022 where an individual purposely, they generated data and then they said, okay, let's misspecify what our prior information is and see how well we can do. And they found that, misspecifications of the prior model that were kind of in a similar functional form, say, let's say the underlying thing had a positive square root, but you had an exponential function there, right? They found that does actually improve the predictive performance, even if you have a small misspecification. It's kind of interesting because it means that as long as you kind of are pushing in the right direction, it does seem to give an improvement. Though it's hard to prove that happens in general, right? I mean, what we've seen now is just I think that the YouTube video is just like that the JuliaCon video, and I think they even put a paper out on this. They just have a lot of these different case studies that show it seems to be working out, right? I do. There are some studies that we did that we didn't publish that were kind of interesting. So one of the things that we did was with the one of the things that we're looking at, especially in the biological and pharmacometrics context, is if you assume that there's a chemical reaction in your model and it's not actually there, and you use this neural network, will it learn to essentially negative out that term, right? And then if you do the symbolic regression, you find that you have minus of a term that did actually exist within your model. We did see that did tend to happen. We never really finished that work, but that is something that if you go and you do this process, you'll see that it will, in a lot of cases, learn to minus out some of these terms that exist before. And so, in some sense, that means that if you know that your model is supposed to be prior correct, you should find some ways to kind of regularize that behavior out. Or B, if you really don't know if you should trust your current model, like in a lot of biological cases, it seems like it could give you a way to be able to point to chemical reactions which are a lot less well motivated, which that happens all the time when doing these kind of chemical reaction network models, right? Where you sift through literature of 50 papers, and one of them says, oh hey, CRABP2A most likely upregulates CYP256 or something, and you find no other papers that say this. And if you do this, you start to find like, oh hey, the machine learning is telling me that this term might not actually exist, right? And so how many times it will actually subtract it out, it's very hard to quantify how often that works out. But we have seen that, on constructed toy cases, that it can actually pull that out. Yeah.
The thing that's really interesting about that is that's a really cool result, and I absolutely believe it. I think the question is like the data efficiency aspect, which is if you the more correct your mechanistic model is, the more data efficient you're going to be. And if you get to the point that it's incorrect, the neural network might be able to recover, but you need more and more data. So finding out the frontier of when you can start to use these methods and so forth, I think that's really, really interesting.
Yeah, and so I think that this picture is simplistic, but I think it kind of captures this kind of high level idea, which is that you really just need there's like an information meter, right? If your information meter gets high enough, you start to get good predictions, right? And your information can be in the form of data, or it can be in the form of correct models, right? It doesn't really matter how you get there, as long as you get to the right mixture, you start to do well. We had a paper with Sandia that started to look into the data efficiency of some of these scientific machine learning methods. I think I forgot to mention this in here, but what we did was we just looked at a lot of different cases where we said, okay, as we have more and more correct model specification, how does our extrapolation performance with less data improve, right? And we start trying to show that in some empirical ways that this trade-off is really happening, right? And so it really then is more of like this kind of loose trade-off where you can start to say, as my prior model is more correct, I can rely on using less data, right? Now, how much is exactly how how do you actually measure model correctness? It can be difficult, and how to know whether you have enough data is difficult, right? But the general idea seems to hold, and I think that's the right thing to keep in mind. Yeah.
So if I may reinterpret what you're saying, it sounds like you're proposing one strength of this is a hierarchical learning thing where you have symbolic regression, scientific theories that space is not differentiable. Possible scientific theories, there's no derivative on those. But if you propose one, you can use your derivative to search efficiently around that one and then propose another one, another one, another one. So you speed up the search over a non-differentiable space of theories.
Exactly. Yeah. So I've referred to this before as almost like simulated annealing of missing functions. So you kind of push everything to this continuous space where everything's just differentiable, and you just do this finding a neural networks of parameters in a nice continuous space. But then you start to say, okay, after I've learned something, let's anneal it back down to there must be discrete terms, and what are they, right? And the real key here is that if you're to write out all the different possible terms that could be in your model, right? Because you could say, well, what if you just wanted to do an L1 nonlinear regression here, or you just write down all possible polynomial terms that could show up. It gets unruly really fast, right? So you have to write down, say all cubic polynomials, but then you have to also include, your cosines, your sines, oh, maybe there could be trigonometric functions in here. This discrete space of possible functions is really large, but the space of the space that continuous neural networks can represent is fairly large as well, right? So yeah, we essentially use the continuous form to kind of find what's going on in our model, and then we can pull it out and analyze it in isolation. And this comes into play. I'll get to the pharmacometric modeling case where this really comes into play, where you don't necessarily have another way that you could have done the sparse regression. In this exact case, there are some ways to be able to do the sparse regression on a simple ODE with fully observed data, kind of, but this idea, can go, you can start to apply this idea in cases where you may not have necessarily known how to do the sparse regression any other way, right? And so so I like to think about it as like almost an annealing process there.
That makes sense. Thank you.
And so all those things kind of described what's going on with ODEs, but really the kind of the core of what we've been doing a lot with SciML is allowing people to make use of these models that go beyond ODEs, right? Because that's where you start to get a lot of very interesting behavior that you can then start to include in your models that are not necessarily the simplest of continuous processes. So one example of this is the simplest extension is to use partial differential equations, where you see this group they use the same software, the same technique, and everything. Where instead it's using a neural network within the PDE definition. What they then did was they took a semi-discretization of the partial differential equation, and what you get from that is ODEs, and then you can then do the identification of the neural network on the resulting ODEs with the interpretation back to this PDE definition, right? But the same general idea kind of formed. And in fact, one case that is still not too public that in which we were doing this sort of form. At Julia Hub, we were working with the Williams Formula One team on improving their ability to be able to predict car orientation from these onboard sensors. And what we were able to show was that the scientific machine learning type of method, with some kind of physical processes baked in. I can't mention too much of it, but I mean it's a very much the same idea as a lot of what we've been doing with these universal differential equations. What we're able to show was that using this type of prediction approach was able to greatly outperform these kinds of Gaussian process regressions which were being used before, right? So in here we showed that the prior model was this Gaussian process regression in Python. This one, and then a more physically motivated version, which used a underlying mechanical description of the system, augmented with a neural network. Was able to give much better predictions of the car orientation. So we've been seeing this in all sorts of examples, and including when PDEs start to get involved. I'm going to skip over this a little bit, but really what we've been doing in the scientific SciML organization is really then allowing people to have a full ecosystem of tools where you can start to place neural networks in, nonlinear solvers, differential equation solvers of, with delays and stochastics and all these kinds of things. Basically, if you have a mathematical model, you might want to put a neural network in there, and then it's really making sure that the whole modeling ecosystem can support that.
Actually, question about the ecosystem. Is this all for Julia-based solvers, or can I shove something? I mean, I have a DOE physics solver written in Fortran. What do I do?
Yeah, so if you have a DOE physics solver written in Fortran, you can make use of a tool called Enzyme that can handle some Fortran that could be compiled via L-Fortran. Though, yeah, it really depends, right? I'll get to this whole discussion of adjoints in a little bit. That'll be this next part. Well, after this part, yeah. So I'll punt on that and I'll come right back to it.
Thank you.
Yeah, so a side dive here is, what are some problems that you can use for this and solve with this kind of technique, which can be very difficult to derive alternative algorithms, right? So if you go back to this kind of symbolic regression to find ODEs, there are people that have been able to come up with methods for doing symbolic regression specifically for ODE systems from time series, right? That's not new. But I think that the interesting thing here is that this idea of using neural networks to be able to capture missing functions and then be able to analyze them in isolation, right? That is a generalizable idea. So what I want to do here is I really want to dive into one of our real use cases where we've been extending this idea, where there's not even really a clear alternative method, right? And in this use case that we have is with the nonlinear mixed effects, or deep NLME. And so deep NLME is nonlinear mixed effects modeling is something that's used in clinical pharmacology. It's used to be able to understand how different individuals will react to a drug within a clinical trial. And so I think that the best way to understand a nonlinear mixed effects model is to just kind of see a simple one, kind of a introduction by example. So the core to a nonlinear mixed effects model is that there are some information that you can know about a patient the moment that they walk into a clinic, right? So these are called your covariates. Things like the patient's weight, their sex, certain genetic information, these kinds of things can be used as essentially prior information about the individual. And your covariates then inform something called the structural model. So the structural model is some kind of nonlinear model that kicks out parameters, where these are then parameters of a dynamical system, where this dynamical system then is modeling the drug dynamics within the body, right? And when you do this within a clinical trial, you can measure what the covariates are, and you can measure the internal drug dynamics. And now the key here, though, is that in the structural model, there's kind of two different parts. There are these thetas, which we call the fixed effects, and the eta, which we call the random effects. And what we want to do is we want to find, the fixed effects, or basically the average effect of a covariate on these parameter terms in the dynamical system. And this is the nonlinear mixed effects estimation process. And the way that you do that is you say, well, I want the random effects to be a per subject kind of effect. And so therefore, they should have no average effect. No average effect, meaning that the expected value of the eta over the whole population should be equal to 0. And so the estimation process of the nonlinear mixed effects is essentially find the values of eta such that the expected value of the eta is equal to 0, and the predictions are matching the dynamics of each individual in the population, right? So you're really trying to find, what is the biggest effect that I can attribute to, weight and sex that are not individual specific. And so this is something that's done all throughout of clinical pharmacology. And the thing that really became interesting with this was that we actually started working, started doing a lot of this work on scientific machine learning at the same time that we were working with Moderna on the COVID-19 vaccines, right? So one of the other jobs that's mentioned in my titles there is I'm the director of scientific research at Pumas AI, which builds software for nonlinear mixed effects modeling. And so we're working fairly closely with the therapeutics group at Moderna for the development of for the development of the dosing regimens for the COVID-19 vaccine trials, and then eventually the translation of those from the adult to pediatric, right? And really the key there was really, if you have one of these nonlinear mixed effects models, you can start to do predictions like, well, if I change from adults to pediatric, then how would I expect the internal drug dynamics to change? And so therefore, how should I be dosing the individuals differently, right? So it was really trying to predict what should the starting dose of these clinical trials be, so that way we get the clinical trial right the first time. And the thing that was really interesting about this process, right? We've, as a mathematician, computational scientist, we spend so much time, trying to improve this performance at which we can do this nonlinear mixed effects modeling, right? But if you actually take a look at, what happened throughout this process, and it seems to happen for every single type of nonlinear mixed effects problem that we run into, most of the time was actually spent on trying to find these predictive models, right? So, like 6 months of the process is coming up with good predictions for what these structural models and these dynamical systems are. And then, they could take, say, 2 weeks to be able to train on a very large data set. That's not really the key, right? The key is the scientist time, which takes 6 months, right? And so what we started to look into was, well, can we improve the scientists, time? Can we improve their time to be able to come up with predictive models? And of course, the answer then was this universal differential equation technique, which we were developing, simultaneously at this time, right? So then what we're able to do then is able to say, well, we can take the same idea of a UDE, but we can now do this within the context of nonlinear mixed effects. Now, how you do that is you have to kind of interpret the neural network parameters as fixed effects, and then you do this maximum likelihood procedure. So you do this kind of special maximum likelihood procedure that you would have done with a nonlinear mixed effects model, but you do this where you now have neural networks as part of the functions in here, and you treat the neural network weights as fixed effects. And so everything that you had as part of your nonlinear mixed effects fitting regime is kept in place. But now, if you do it under this interpretation, you can essentially model these unknown functions. And the interesting thing here is that there's no way that the FDA is ever going to accept a structural model that has a neural network in there, right? Because, well, I mean, the structural model kind of, in cases which succeed through the clinical trial, the structural model is actually telling you, this information of how you should be changing your dose with respect to, if a male versus female and different weights and such, right? And so the FDA is never going to allow you to be able to say, well, in order to find out your dose, please run this neural network, right? Maybe in the future, but that's not accepted right now. But what you can do is you can say, well, once I've done this process of finding the missing functions of this, nonlinear mixed effects model, now I can pull this neural network for the structural model out in isolation, and I can say, well, what's the most likely functional form that could be in there, right? You can do the sparse regression and can put you in the right general region. And then you can use this to be able to, say, find corresponding research that tells you, yes, we would expect that, sex changes the clearance of a drug that has this certain capsule, right? Or sex does not affect the clearance of the drug, whereas, the underlying gut volume and, these things all have a meaning, but this can put you very close to what the meaning should be and give you these predictions, and then kind of improve this process in the speed at which you can get to a predictive model. Right. So at the end of the day, what you have is you would still end up with a mathematical model that does not have a neural network in there, but the neural network can be an intermediate that can get you there faster. This is actually something where, since we are the ones that were building the software that these groups are using, we started to work at these neural networks into there and be able to say, okay, let's extend the nonlinear mixed effects framework to have these neural networks. So you can say, now I have neural domains, and I can train these neural domains. And this is actually what we're now trying in clinical trials. So there's some ongoing clinical trials which are testing whether this kind of technique can improve the clinical trial process. And so it's still ongoing, so I can't give all the details on that, though I can say that it is seemingly improving this process. In fact, our group at Pumas recently won an award at one of these pharmacometric conferences for some of the demonstrations showing that it has been learning individual patient predictive models. So I think that this is kind of like a case study that shows that this kind of scientific machine learning technique is really starting to bridge from, just like these toy academic cases to things that are useful in the actual industrial practice.
So let me really poke at the value of this, because this is kind of like gets at the core of the scientific process. The skeptical way of describing what you just said is, well, you take a neural net, you turn it into a linear form, and you find excuses for why the linear form is the true thing, even though it's just an approximation. But it's not. I think it's unfair. I think what you're really doing is saying there's a whole ton of data sets out there and research that's not part of your training set and you have no access to, but really are excellent samples of the truth, just not available. So what you're doing here is breaking it down to a form to say that data set justifies this subterm, and if you cannot find a data set, toss the term. It's a bad approximation. But now this is a way of extending the reach of the data that's available to you to the wider literature, whereas if it was a neural net, it's stuck in the one data set you haven't had. Is that fair?
Yeah, exactly. Yeah, I mean, it's really this problem of, especially when you're doing this, like, systems biology and clinical pharmacology, right? There's, there's so much research on there about how, this capsule can, affect clearance or the reaction rate inside this body. And there's so much research out there, but, these days that, if you know what to kind of look for, you can find it, but it's fairly difficult to know what to look for, right? So, the way that people did mathematical modeling, like the way that I did, biological modeling in my PhD, like the starting point is, you do a literature search through, 4,000 papers or whatever. You're just like, okay, let me try to find everything on, the zebrafish hindbrain, right? You just try to search through that, and then once you hope you found everything, and then you start to go, these are things that people seem to know here. So now let me start to put some arrows down, draw some arrows, and build a mathematical model of that, right? But it's a very labor-intensive process. So what this is really starting to do is it's really starting to say, well, if you've done some of that, great, start there. But now this can tell you, oh, most likely with what you've written down, you're most likely missing an interaction here, right? You're most likely missing an interaction between weight and the clearance of this drug. And so then you can, once you kind of know that, hey, this is most likely what I'm missing, you can start to Google around, and you might even find, see study 1, study 2, where you find very similar capsule chemistry is giving you this exact behavior that weight. It's a weight dependent response, right? And then you can go, oh, I have found, this, so it's not that it's telling you exactly what needs to be in the model, but it's telling you where to look, right? It's if you think like ChatGPT, right? ChatGPT is not necessarily correct, right? But it kind of can help you kind of be like, oh, this should be about correct, and you got to go correct it yourself, right? This is essentially what we're kind of doing to this nonlinear mixed effects modeling process here. Does that give a good description?
It does. In fact, I do not notice that you can't feed these suggestions in ChatGPT and say, find me papers like this. What the follow-up is, this is, again, this is a core science question. You're now making more efficient to find justification for your terms, as well as lying to yourself about the validity of that justification. Any thoughts about how to control the degree of, well, lying to yourself?
Yeah, I mean that is a difficulty, right? That if this does not point to a term that is in there, and then there could be some literature that says that some extra thing is that you're not modeling is in there. Yeah, we don't really have a way of if this isn't capturing a term, and then it's not going to lead you to that term, and that is kind of a bias, right? So you do need to make sure you do know the literature enough, so that way you're not leaving things out. That is something that is true. And yeah, I mean, one of the ways that we are looking into, I mean, so the without going too deep into this whole pharmacometric software, one of the things that we have been looking into is there is something that's called optimal experimental design that's as part of this. And optimal experimental design essentially lets you design what new experiments would tell you whether certain parts of a whether certain parameter values are likely correct or incorrect. It can give you the basically some of the clinical trials studies that would most differentiate different parameters. We're trying to come up with extensions of that to this UDE case, or optimal experimental design methods that would most likely be able to differentiate different terms that come from this neural network, or whether things are missing. So I do think that there needs to be an extra step there to be able to guard against that. I don't think that we have that all worked out right now.
Yeah, that makes sense. Thank you.
Yeah, I think that the key here though is that the scientific process is non-static, right? I think that when we think about a lot of these methods, we always think, I have this data, and so therefore I go to, I do this and it gives me this prediction, right? But the scientific process really isn't static, and so when we start to think about it in this context, when we're really working with these real individuals, right? You take the data you have now to come up with, what did I not know about the model, and then once you come up with those things, the real thing is, what is the next experiment that I should be doing to be able to then improve the model more? And then what's the next experiment after that? And, when you start to think about it in this iterative process, right, it's more about, as you said, scientific debugger, helping someone through this iterative process and trying to make it more, trying to give them motivation for doing some, hopefully correct actions much quicker, rather than requiring that someone has read, the entire literature and memorize it all the way through, right? That's really the key here. Was there another question that showed up in the chat there?
No, it's just a comment about some internal alphabet things.
All right. Yeah. Next piece here is, doing such methods require differentiation of the simulator, right? So I'm getting closer to time here, so I'm not going to be able to. I'm going to go through this a little bit fast, so that way I can make sure to get to the stochastic AD portion. But I think that this is one of these key pieces, right? So we have a very nice study on this that comes from this case on high fidelity surrogates of ocean models or columns for climate models. So this was really a case where we wanted to be able to use a UDE type of form to be able to come up with one-dimensional PDEs that are good predictions of the three-dimensional Boston-Nest approximated Navier-Stokes equations. There is a 2022 version of this paper that goes in a lot more detail than the 2020 version, if you want to kind of dig into it. But the key idea is that the way that you would normally build these ocean columns within a climate model is you would take the three-dimensional Boston-Nest equations, you would take a integral along the xy plane to be able to take an average out through the horizontal plane, and then if you do that, the first terms of your Taylor expansion is everything but this neural network. Normally what you do is what you call the convective adjustment, which is this equation without the neural network. You may call the higher order terms equal to 0, but now we're going to say, let's capture those higher order terms with this neural network, right? And so there's essentially one way that you can fit this without having a simulator in the loop at all, right? So what you could do is you could say, well, if this is my model, and I have a three-dimensional simulator for the temperature changes in this ocean column, I can take my temperature fluxes, the average horizontal temperature fluxes. That's supposed to be this dt, right? I can then calculate out all these other terms. I can find out what my residual is, and I can directly fit the neural network on the residuals against each of these data points, right? And so I could essentially take my data, I can pre-process it towards this neural network, I can fit this neural network, and then stick it into a simulator and see how much this correction has helped, right? And if you do that, you see that you don't really get that great results. You tend to get this drift. And actually, it's very interesting, because one way that you can understand this drift, right, is actually very similar in control theory, where if what you do is you can think about this neural network as trying to control the derivative back to its correct values, right? So it's almost like a controller where you know what the underlying derivative should be, and this is supposed to be driving it back to those correct values. And then this training process is essentially training it so that way you can find the right derivative control to be able to push it back. And if you know your control theory, if you only are doing derivative control, you get this drift over time, right? And one of the ways that you normally would fix this in a controls context is to, instead of trying to make the controller correct for the derivative, you try to make it correct for the integral, right? And so correcting for the integral would mean that instead of trying to fit this neural network in isolation and then putting it into the simulator, what you do is you say, well, I want this I want to be able to fit this this model of the temperature in this ocean column. And when instead of using the derivatives of the temperature values, I want to use the temperature values themselves, right? If you do that, then you actually calculating this temperature value requires being able to put these neural networks inside of the simulator and doing these full simulations, being able to do these full PD solves and such. And so therefore you need to be able to differentiate PD solves as part of the loss function. But you find that this really gives you, orders of magnitude better predictive performance, right? And so, there are ways to be able to get around having differentiable simulators, but they just don't seem to give the same amount of performance in the end. I think that that's really the key there, right? So, really ending up at time here, I want to kind of skip ahead, right? So there's a whole section on differentiation and adjoint methods and such. Key there is that there's more than one adjoint method, and there's things that you need to be aware of with numerical stability. But I want to kind of get to this one piece here, which is about, can we generalize this beyond continuous models, right? So someone mentioned here about doing scientific machine learning with agent-based models, right? And so we started trying to look a lot into this. So we had a paper at NeurIPS 2022, which is called Automatic Differentiation of Programs with Discrete Randomness, where the key idea behind it is, in traditional automatic differentiation, you try to differentiate a program by taking a deterministic program that is a function of your parameters, and you try to build a new deterministic program that when you run this program, it gives you the derivative of your original program with respect to the parameters, right? So what we do in this case is we say, okay, what we want to do is we want to take our simulation now as a random variable, right? X of p. And we want to build a program that is a new random variable, x tilde of p, where when we take the expected value of x tilde of p, it should give us the derivative of the expected value of our original program, right? So there are some ways that people have looked at in like reinforcement learning literature where they try to do continuous approximation and such for the derivative. But this is really just saying, if I have a stochastic program, can I build a new stochastic program that has properties that are matching the derivative? And this is a nice generalization that gives you some very nice properties. I won't be able to go over the full derivation here and such, but what comes out of this is you can come up with a extension to say forward mode automatic differentiation, which is then this kind of stochastic triple, where when you run this stochastic triple through a program, you basically take a program that has discrete randomness and generate a new program that has discrete randomness, where you can think about it as, let's say you had a binomial, you have the probability of having 1, 2, 3, or 4. You can now say that I have a infinitesimal probability of having also an O of 1 change in my result. Infinitesimal probability of having an extra value. The binomial was +1 or the binomial was -1, right? And so you can take what you would do with, like, say, dual number arithmetic and forward mode automatic differentiation and extend it to this case where now it's generating these new stochastic programs that can then differentiate programs that are, for example, take the derivative of the probability of getting a heads with respect to a Bernoulli random variable. And with this kind of work, what we've been showing is you can use this to be able to get derivatives with respect to expected values of agent-based models, in particular things like stochastic game of life, and then be able to use this as then a basis for then training neural networks that capture average behavior. I think I'm a bit over time here, so I just wanted to make sure I ended on that note. And if anyone has any other questions, there are some things that I've kind of skipped over, and so I'd be happy to kind of chat about any of it.
All right, well, thank you very much. I mean, I don't know if you have any more time to chat after this. Okay, Chris, do you have any more time to chat, or do you have a hard stop?
Yeah, I do have a bit more time, yeah.
Well, then let me ask you something. So I guess I'm trying to capture the core ideas as opposed to just the current software framework. If you had a random piece of code to do stuff with, what would you need about it? I mean, is it like, to give me a derivative in a piece of code, then I can do a lot of this magic, or what would you need?
I mean, that's really the key. So in this last piece, right, I kind of skipped over a little bit, but when you do, for example, chemical reaction modeling, right, there's all these different cases where you can look at it as mass action kinetics as an ODE, or you can look at it as something that has continuous randomness with the stochastic differential equations, or you can look at it as something that has jump processes, right, where everything it's modeling chemical reaction X plus Y generates a Z, right, and then degrades back down to X plus Y, so everything is discretely valued, right. It doesn't really matter where you are in these cases. There's a very similar idea of, for example, there's a reaction rate, right? Or reaction rate functions. And what you want to do is you want to, figure out what your reaction rate function is, because if you know your reaction rate function, then you can predict, how much of this chemical reaction would happen, right? And it doesn't really matter which mathematical form it's in, though. So some of these forms actually can capture information better. So, for example, the Poisson continuous time Markov chain process, it's using these discrete values. When you have values close to 0, right, the difference of 0 versus 1 is huge, which the stochastic differential equation does not accurately capture, right? This kind of a low copy number problem in systems biology. And so what we're really trying to do is say, it doesn't matter what kinds of models you're looking at, agent-based models, or discrete chemical reaction networks, or continuous chemical reaction networks. If you can find ways to be able to differentiate them properly, right? Differentiation is required because of this kind of property that fitting with the simulator tends to outperform not fitting without the simulator, right? But if you can differentiate any of these types of simulations, then you can start to very smoothly integrate neural networks into them and start to say, well, I have an agent-based model or a chemical reaction model. I don't know this function. Well, let's make that function be a neural network. Do this whole process. Once you grab that neural network in your agent-based model, you can pull it out and say, well, sparse regression, and what should I have put there in the first place, right? So it's almost like, if we can get this down in a very general context, then it could be a very nice, smooth way for helping people build models faster.
Okay, so if I were to make an API, it sounds like, give me your derivative for this chunk of code. That's an API. It sounds like expose some parameters and run the program, like for the stochastic thing, run it a million times so I can get a probability distribution. The API is just, let me control some of your parameters and let me see the results, right?
Yeah, I mean, it also requires that say, I mean, I guess that's a very high level version. I mean, in current practice right now, one of the things that is kind of required is that the user does need to supply, say, a neural network, so that way, you have to kind of put a universal approximator in there. And what is a good universal approximator is, the whole question of machine learning, right? And so we haven't found a good way to be able to model to automate that process yet. But yeah, in theory, we could be able to say, build a modeling platform where someone just says, I don't know what goes here, right? And then it just kind of, you can almost think AutoML. If you have derivatives and you have AutoML, it could train a neural network to be there, do a sparse regression, and then put the right function back in there.
Right, and that's, I mean, where I'm going with this is, Julia is a powerful and growing ecosystem, but most code is going to be written in God knows what, and people are proposing new frameworks all the time. If you have a few primitives that you just instrument your program with, then maybe a lot of these drivers can just transform any program.
Yeah, and a lot of these, differentiation tools can start to say, well, if you do this function call, what is the derivative of this function call, right? As long as you can be able to find the derivative of your arbitrary function call, then you're fine. So there's, I think that one of the people who works in automatic differentiation on some of the Julia libraries has shown that you can put a derivative definition on PyCall, right? So that way, when you do a call out to Python, it asks PyTorch what the gradient is on that piece of code, right? And in that way, you can start to do this cross differentiation, and it works out pretty smoothly, right? So yeah, as long as there's ways to be able to hook up different derivative calculation tools, it'll start to work out fine. But I think that the key, though, is that the previous scientific stack of we have these these hard-coded things that don't necessarily have adjoints with them and such. That's what we got to start to say is oh, we need derivatives on every if you have something in your simulation, you need to be able to differentiate everything. Doesn't matter if it's even even if it's calculating a binomial with with parameter p, right? You need to be able to differentiate that with respect to p. So like every piece of everything that you're doing with your simulation needs to be able to take a derivative. If you could do that, then these techniques really just kind of start to flow.
So let me just take a page out of a few slides ago. If I simply gave you the API, if it hemorrhaged a bunch of intermediate states of the simulation and you trained a neural approximation on that, it's a mediocre derivative, better than nothing.
Mm-hmm.
Would that work even if the code was not instrumented, with a proper adjoint, which requires thought?
Yeah, I mean, to an extent, there is an issue where in some, especially in some of the behavior, I think that actually some of the best examples of this is some of the papers about the development of Pumas itself that kind of went into some properties of if you have too much incorrect derivatives, this was just for the maximum likelihood estimation. If your derivatives are too incorrect, it can lead you to these bad local minima very easily. And things like DFDS can kind of run into issues if you have too much noise, where that noise is due to finite differencing and such. So yeah, so to an extent, yeah, I mean, you can finite difference your way out of certain pieces, but the numerical stability issues actually are kind of, that's what's kind of hidden within this whole talk. So I have this paper called Stiff Neural ODEs, which kind of goes into a bit more detail of some of these issues, which really starts to talk about how we gloss over the numerical stability of a lot of these derivative calculations, but a lot of the ways that we calculate these derivatives are actually unstable. And if you don't take that into account, then there's a lot of cases where this simple process of even just differentiating an ODE using an adjoint method, it can lead you to bad results because your gradient just has too much noise, or it could even be divergent, right? So so in theory, you can do the easy gradients everywhere. In practice, you have to worry a lot about the numerical stability of the way that it's being calculated.
Okay, that actually makes a lot of sense. Let me ask something in a different direction than the tools. Especially in pharmacology, you need to have, all the economists and public health people, they develop all the suite of causal inference methods to stabilize your learning in cases very likely where the process of observing a sample is correlated with the process you're trying to model. Have you looked at using treatment effect estimation, all that literature to train these models better? Or more stably, I guess?
I have not looked too much into the causal modeling literature, though I do know that this is one of the next things that we probably want to be integrating. Yeah, that question has come up before, and I think that that is probably once we have a PhD student who's interested in SciML and causal modeling, that's definitely going to be a topic that comes up. So I'll punt on that for now and say I don't know enough, and hopefully I will know enough in the near future.
Okay, no, this is very promising because I guess as somebody, like Miguel Hernan, I think it was, who said this, you're trying to find a randomized controlled study in your actual data set. And in practice, if you steal enough of these ideas, it's practically like just give me a random model and I can stabilize it. So that they are fairly decomposable, conveniently enough.
Yeah, I mean, and I think that the reason why we've kind of avoided it is just because a lot of what I was doing this development was when we were working on Pumas and we were working with Moderna, and we do have these randomized controlled trials, right? So since my actual use case for developing a lot of this had randomized controlled trials, that kind of issue of can you automatically find real trials within the data that you have. That wasn't an issue that we had, so it wasn't an issue that we addressed with the methods yet. But definitely, we've been working somewhat with some macroeconomists, right? We did some work recently with doing things like Hamiltonian Monte Carlo on these DSGE models, and as we start to get to that kind of modeling regime, that's definitely a case where you can't do a randomized controlled trial, and so that requires new techniques to be involved, and we haven't opened up that whole can of worms yet, but it's at our doorstep.
All right. Well, nice. Thank you. Does anybody have questions on the call? Well, I think we're set. Yeah. Thank you very much for coming. This was fascinating. Fantastic.
Yeah. Thanks so much for having me.